One of the things that's important with solutions is the way that we make them, the way that we prepare them. And sometimes when we're given starting amounts of a solution, we have something that's more concentrated than what we want to work with. And so if we wanted to get to a lesser concentration for our solution, we would perform what is called a dilution, which is just adding water to an aqueous solution to change the concentration, to get it down to the concentration that I'm looking for. So if I have this solution here, it has a certain number of moles of solute, right? So whatever the initial number of moles of solute, let's just call that X for the time being. So there's X number of particles that are in solution, and I have a specific volume, and I have some sort of initial volume here. So let's call that V initial is how much space this is in, milliliters or liters or whatever it is that I'm measuring in. So if I wanted to figure out the molarity of this, the concentration of this, I would take the moles divided by the volume, and that would give me the concentration. Or I could say that the moles are going to be equal to whatever that initial concentration is times that volume. So that could be M initial times V initial, or sometimes you'll see this as M1V1. So whatever the concentration is of this initially times whatever the volume is of this initially is going to equal some amount X. All right, that's pretty straightforward. So this is the number of moles that I have. Now if I'm going to add more water to this to make this more dilute, so I add some liquid water to this solution, and now I have a new volume. Then kind of here was my initial volume. Here's kind of V initial. Here's my final volume, or maybe V final, or V2 if we wanted to call it. Ones and twos, initials and finals, you'll see it both ways. Then the only thing that's changed between these two things is the amount of space that it takes up. The number of particles didn't change, so I still have X moles of solute, right? That's the same. But what I've changed is now I have this new condition, this V final or this V2, right? But since that's still equal to X, right, then whatever my V final has to be times whatever that new concentration is still going to equal X, because I didn't change the amount of particles that I had in solution. Or we could kind of call that kind of M2V2. So this is our dilution concentration calculations, kind of M1V1 equals M2V2. And so what we're saying is that because the number of moles doesn't change, I didn't change how many particles I had in solution, I just changed how much space they had to swim around in, essentially, then I can set these two quantities equal to each other, right? Because the concentration times the volume gives you the number of moles. And if that number of moles is the same, then I'm setting them equal to that same value. So if this was 5 moles, then this would equal 5 moles, and this would equal 5 moles. So, because of math, then I can set these two things equal to each other. So M1V1 equals M2V2, or M initial V initial equals M final V final. You'll see it both ways. I kind of like the ones and the twos because it sort of mirrors the gas law setups, as well as sounds like Star Wars robots, which I think is an important feature in a mathematical equation. Okay, so with a dilution then, we can solve problems that look like this using these calculations. So our lab tech has a 12 molar stock solution of hydrochloric acid. So when we get chemicals in our stockroom at the school, then we usually get very concentrated solutions, and then we make them into more dilute solutions for whatever we need for our various situations. So whichever labs we're doing, we have different concentrations. So let's say for our Chem 121 students, we need to make 2 liters total of 6 molar HCl, and we're going to divvy that out between the students in order to do an experiment. So how is the lab tech going to make that? Well, we can use our M1V1 equals M2V2. So we should figure out what we're given to start off with and kind of what information we know from this problem, because that's always a good way to go. So here's my different variables, V1, M2, V2. So let's figure out what we know. We know the initial concentration of my solution because we said we had a 12 molar stock solution. So that 12 molar stock solution is my initial concentration. I want to make 2 liters. So if I want to make that, that must mean my final volume. And that 2 liters of solution needs to have a concentration of 6 molar HCl. So that's my M2. And then it's asking for how many liters of stock solution did I need to start with. So that's kind of my initial value. So when I'm solving my problem, this is what I'm going to look for. So if I rearrange this to solve for the variable that I'm looking for, that would be my V1, M2V2 over M1. So if I plug in my values, here's my 6 molar times my 2 liters divided by my 12 molar stock solution, then that's going to give me 1 liter, right? Now this kind of makes sense from just a conceptual standpoint as well. So I'm going from a concentration that's halving, right? So I had a 12 molar concentration. I'm going down to 6 molar. I want 2 liters of solution, so what would I need to start with? If I'm having this, then I must be having this, right? They're kind of proportional to each other, so it would make sense for me to have the 1 liter to start off with. Now, how would he go about physically making this? We have some cool glassware in chemistry, just sort of in general, but we have some cool glassware called volumetric flasks or volumetric glassware. And it's kind of neat looking because unlike our beakers and our Erlenmeyer flasks that have kind of wider mouths and lots of graduations on them, a volumetric flask has kind of a bulbous end, and actually all of the volumetric glassware has a bulbous part to it and 1 line, and that 1 line is super precise and it tells you the exact volume at that line. And so at this line on this flask, if we were going to make this, this could be my 2 liter volumetric flask. So if our lab tech was making a 6 molar solution using that 12 molar stock solution, we would take that 1 liter of stock solution and we'd put it in our volumetric flask. So we take 1 liter of the 12 molar HCl, and then we put it in there. And so you have, you know, the 1 liter worth, and there's your 12 molar HCl. Now you're going to add water to this, to that line. So you're going to fill it to that line so that the line of the water is right there. Then you're going to, meniscus is right on that line. And then you'll just add the water to fill it the rest of the way and mix it as you go. And so if you have this mixed solution, then the amount of water that you're adding is going to give you that new concentration that you're looking for. And this is the dilution. So here's your stock solution. Once you have that stock solution, the number of moles doesn't change. You're going to add water to it so you have a new volume. And so what changes isn't the number of moles, it's the concentration. And so this is really useful and has a lot of cool applications in chemical solution making in stock rooms and all that kind of stuff. If you have any questions on this, don't hesitate to ask. Otherwise, I'll talk to you again soon.